Welcome to the NHERI SimCenter's Live Expert Tips. In this session, we will introduce you to multi-fidelity Monte Carlo simulation as a means to efficient seismic risk analysis. Our expert today is Dr. Song-Ri Yi. She is a researcher at UC Berkeley, where she develops novel methods for sensitivity analysis, multi-fidelity surrogate modeling, and adaptive design of experiments at the NHERI SimCenter. She received her PhD in civil and environmental engineering from Seoul National University. Her research interests include probability-based sensitivity analysis, surrogate modeling, structural reliability, and random vibration analysis. Song-Ri, thank you for being here.
Thank you, Matt. Thank you, everyone, for coming to this live expert tip. Today, I will talk about multi-fidelity Monte Carlo simulation with an application of efficient seismic risk analysis. So before we start, among 6 of our SimCenter tools, this presentation will use EUQ as our demonstration example, which is used to assess the earthquake response of a structure. And there are various modules supported in EUQ, and today I will use uncertainty quantification module for multi-fidelity Monte Carlo, and we're going to also use ground motion generator. But for structural modeling, we will bring our own model, which is written in OpenSys. And we are open source project, so we have our algorithms opened in our GitHub. And if you have any questions, please reach out to us through our SimCenter forum. So let's start from the motivation to perform multi-fidelity Monte Carlo. So let's consider seismic risk assessment example. We have a structural model and we have earthquake excitation, and we are interested in estimating the peak response. The problem is that our ground motions are highly uncertain. And also on top of that, we have like random variable which represent uncertainties in our model parameters. But so to account for this uncertainty, we need to run lots of nonlinear time history analysis. And often we are interested in estimating the probability of the response exceeding certain threshold level. And this can be very time consuming. For example, in this specific example, it needed more than 7 hours to obtain each of these curves shown in this plot. So our challenge is that we have a model which is very expensive, so we cannot run this so many times. But if we try to estimate statistics like mean or variance using only few number of simulations, we will necessarily have a large variance in our estimation. So we don't want that error to come in. So an alternative approach we can take is to have another model, which is a bit simplified, so it's not as accurate, but it runs really fast. So with this model, we can run much more number of simulations, and then we can really precisely estimate its mean and variance of its response. But the problem is the model is not as accurate, so there is this bias which exists, which cannot be reduced by adding more simulations. So our question in multi-fidelity Monte Carlo is that, can we use information from both simulation results to arrive at a best prediction? Best meaning we have smaller variance and also we have unbiased prediction. And this is addressed by introducing multi-fidelity Monte Carlo simulation. So how multi-fidelity Monte Carlo works is by learning correlation between high and low fidelity model. So let's consider a case where we have a very good low fidelity model. Then if we compare the response from high fidelity model and low fidelity model, the point in the pair plot will lie on the diagonal line, almost on the diagonal line, because our prediction will be very similar. So this is the case where we have a good model, and when statistically speaking, we can say that these two response from high and low fidelity models have a very high correlation coefficient. On the other hand, when we have not when our low fidelity model is not as good, the points will be deviating from the diagonal line. So here we have a lower value of correlation. So by this, I want to say that the correlation coefficient between high and low fidelity models is a good indicator on how good our low fidelity model prediction is. And this quantity helps us to answer questions like how many low fidelity simulations do we want to perform, or how much reliance do we want to place on low fidelity prediction compared to high fidelity prediction. And this, you will see this in our algorithm. So here, the multi-fidelity Monte Carlo algorithm implemented in our tools is summarized in a flowchart. So the first step is to run a number of pilot simulations. That means we don't want to immediately run a batch, like a batch of large number of simulations, but instead we first want to start with a small number of simulations. So we run both low and high fidelity model for some number of samples with the exact same input values. And then we can draw this kind of pair plot that directly compares the high and low fidelity response. And using this, we can estimate preliminary correlation coefficient. And also what we can do is to estimate the average amount of time needed to evaluate low and high fidelity models. And using this two information, we can assign our computational resources to high and low fidelity models. That means we are deciding how many number of simulations we want to perform for low and high fidelity simulations. And this the optimal solution can be derived analytically, which is a function of the correlation coefficient as well as the computational cost it takes to run the low fidelity and high fidelity models. So it's trying to balance between how much gain of information we will get by introducing low fidelity model given some expected time cost. So based on that, we assign the number of simulations and then we run this big number of simulations. So this part is the most time-consuming part of the whole algorithm. And once all the analysis are done, we collect the response from each model and then make the final prediction on our final estimation. So for example, when you want to predict mean of your peak flow drift, this will be the formulation, which is basically the first term is the mean prediction from the high fidelity simulation. And then there is also a term that's related to prediction from the low fidelity simulation. And this row accounts for the correction amount. So we start from high fidelity estimation, and then with this term, we additionally get information from low fidelity simulation and corrects the estimation we had. And additionally, of course, we can get the uncertainty bound of our prediction, which is hopefully smaller than the high fidelity only simulation results, given the exact same resource. And that was the brief summary of our algorithm. The details can be found in our documentation and also in this reference, which also have the derivation on how these formulations were obtained. And then now let's discuss the efficiency of multi-fidelity Monte Carlo. Because multi-fidelity Monte Carlo is applicable only when we have a good low fidelity model. What does it mean by good? It needs to be evaluated faster, much faster than the high fidelity model, but also it needs to have pretty good accuracy, meaning our correlation between high and low fidelity model should be high. So the gain of speed, like speed up, depends on how good this model is. And the most important thing is that multi-fidelity Monte Carlo is not always better than the brute force Monte Carlo simulation using only the high fidelity simulations. So to understand the conditions where MFMC is better than just naive Monte Carlo simulation, we introduced this speed-up measure in this slide, which is basically the computational time saved by using multi-fidelity Monte Carlo compared to only high-fidelity simulations. So that means if our speed-up is 10, that means to get the target accuracy, multi-fidelity simulation will require 10 times smaller amount of computation time compared to the case where we only try to use high fidelity simulations. So as you can expect, this speed up is the function of correlation coefficient between high and low fidelity models, as well as the computational cost ratio. As correlation coefficient gets higher, we get higher speed up, of course, and also as we have as we have faster low fidelity model, we again get the higher computational gain. So let's first consider the case where multi-fidelity Monte Carlo will not work well. That is, let's consider the case where our low fidelity model is only 5 times faster than our high fidelity model. It's still faster, but it's only 5 times faster. And on top of that, our correlation coefficient is only 0.7. In that case, if we try to find the point on this plot, the 5 times means the point will lie on this blue curve. And if correlation coefficient is 0.7, then the point will be around this point outside of our plot. So, and that means our speed up is below 1. That means we are not gaining anything by introducing low fidelity model, but we are losing more by allocating our resources to simulate low fidelity model. So if your low fidelity model is not in a good quality, then it's better to just run the high fidelity Monte Carlo simulation, forget about low fidelity model. But there are cases where the multi-fidelity Monte Carlo becomes a very attractive solution to gain efficiency. And in general, this can be said like when your low fidelity model is like 100 times faster than your high fidelity model. And when your correlation coefficient is greater than 0.95, that means your area, your expected speed gain is covered by this blue area, which can be beyond like it can be 10 times less computational effort if you introduce the multi-fidelity Monte Carlo simulation. And this really tells you that in order to use MFMC, you need to have a good quality low fidelity model. And this is not always possible, but there are approaches that to help you to develop such good low fidelity models. And one example is reduced order models, and different hazard has different definitions of reduced order models. And here I'm just showing one example in the earthquake engineering application. So here, as I will also show demonstration using this example. And in this case, our low fidelity model is a simplified non-linear structural model, which evaluates much faster than our very detailed FEM simulation model. In that way, we can gain computational efficiency, but also we need to have high correlation in our responses. And to obtain that, we need to take a good attention in our model calibration so that our response matches the original high fidelity model. And there was one live expert tip previously that covers on how to develop this reduced order model using SimCenter software tools. So I recommend you to check this out. And the other approach we can take is to use surrogate model as our low fidelity model. Those are just some examples. So now remaining is the numerical examples of multi-fidelity Monte Carlo. So SimCenter application EUQ version 3.4 is used for our demonstration today. So we start from the target structure. We have 9-story benchmark steel building as our target building. And this is moment resisting frame with 5 bays. And our high fidelity, we need two models for this building. Our high fidelity model is written in OpenSys. It uses 5-section model, and the evaluation time it takes is 1 second per simulation, but under 8 processor. So in fact, it takes 8 times longer. And then we have low fidelity model, which is also written in OpenSys. This is basically a stick model, but we have additional springs to that's obtained, the quantity is obtained by static condensation. But to capture the non-linearity, we needed to do some calibration based on the result of high fidelity simulation model. So, and this calibration was done through COFAM based on our previous live expert tip presentation. And then the evaluation speed of this model is was around 1.5 seconds, which gives us almost 50 times of the cost ratio. And then our expected correlation is greater than 0.95. So based on these two information, before running multi-fidelity Monte Carlo simulation, we want to see whether we will get some efficiency by introducing this low fidelity model. So evaluation speed ratio is around 50. That means it lies between this orange and yellow curve, which will be around this one. And then expected correlation is greater than 0.95. So we can see that we will probably get expected speed of around 10, maybe as low as 4, as high as 15 or 20. So that's what we expect. And we can think that this is, then we probably want to run Monte Carlo, multi-fidelity Monte Carlo simulation, because it gives us enough speed up. And just so that you know, we have shared our models used in this demonstration in our documentation. So here is the link to download both high and low fidelity model. So you can find this in our documentation and try out. So I want to now move on to the live demo part of our presentation. Using EUQ tool. So this is the our user interface you can see once you launch the software. So there are these tabs that to help you guide what are the information that is needed to run our workflow. So the first one is uncertainty quantification. So here we want to specify that we are gonna use multi-fidelity Monte Carlo. The multi-fidelity Monte Carlo is implemented in SimCenter UQ, and here you can find it under Monte Carlo. Oh. So this is the, sorry about that. So this is our user interface that you will gonna see when you launch the software. And here you can select the UQ method. The first one is, there are several UQ options supported, but we will run forward propagation under SimCenter UQ engine. There is multi-fidelity Monte Carlo simulation. And the max, here you can define max computation time. In this example, we found we will run 60 minutes because high fidelity simulation takes like a minute. So we need to have enough time. And we can also set random seed to make sure we have the reproducibility. And then it says at least 40 samples will be simulated for each model. That means we allocated like 40 samples as the pilot simulations. So this is the number of simulation that's used for pilot simulation, and you can change this if you want to select the advanced options like this. And then because most of the analysis in earthquake engineering is based on the log transformed EDP. So we also allow the option to do the log transformation for your estimation. And for the general information tab, you can, we will just keep at this as default. This information will not be used. And for this sim, now we need to specify the two simulation models. To do that, there is multiple models options here. And there's one model, we want to add one more model. And always the lower number indicates the higher fidelity model. So here model 1 should be the high fidelity model. And to do this, instead of just the stick model that can be generated by our building model generator, we will gonna import the OpenSys model. And we first import our main Python script, our main OpenSys script, which I located in this folder. And then we will come back to response node, but before that, I also want to import the low fidelity model, which I saved here. You need to only import the main file, the main analysis file, and all the other files need to be located in the same folder. So for the response node, we need to specify which node will be used to evaluate the, say, interstory drift or the peak floor acceleration. Like we need to indicate one node in each floor. So to do that, let's go back to our slides. Here I put the node numbers. Probably you, because you're the model developer, you will know which node to put in for each model. So in this case, for the high fidelity model, we need to say that the ground floor is node number 7 and the first floor is 13, and we can continue doing this until we put all 10 nodes. So that's 10 nodes. And then also we need to do the same for the low fidelity model. Here the ground node is node number 10, and then 1, 2, 3, 4, 5, 6, 9 representing each floor. So after that, we move on to event. There are different event generation options, like we can also select ground motion from peer database. But in this example, we will stick to stochastic ground motion model, and we can set any of these parameters to be random variables, say by changing the number into some alphabet character. And then in FEM tab, again, because we assign 2 models in the simulation tab, we again need to assign 2 models for our FEM servers. And both are OpenSys servers, but we still need to separate them. And for the high fidelity simulation model we have, the default option is fine. So it, based on this information, it will create analysis like script. But for simulation 2, we want to take a special attention because of the structure of the model we have. We want to use our user-provided analysis script, which look like this. So this is almost identical to what can be produced by default option, but we just wanted to put additional option when we evaluate the eigenvalues, which is not supported through our user interface. So if that's the case, you can import your own analysis script in this user interface, and then the EUQ will gonna ignore all the information above that, and then prioritize this script when it runs the analysis. And for the engineering demand parameters, we use standard earthquake EDP, and it's a good practice to use this because in that way the results are compatible to our other tools like PBE or R2D analysis. And standard earthquake means we are evaluating peak interstory drift, peak floor drift, and peak floor acceleration. So those nodes are identified from our specified node in this user interface. And then those nodes will be used to evaluate those response quantities of interest. And in our tab, we have ground motion parameters. I think I wrote down here. Sorry. So how we want to specify our probability distribution function for the variable magnitude. And that is a truncated exponential distribution with exponent of 0.3 and the bounds of 5 and 7.2. And here it's giving you error message when the result is not, the value is not compatible. And you can also see your PDF through this window. It just shows truncated exponential distribution with the specified bound and with the specified parameters. And now, in this example, we didn't put the structural model parameters, but if you want, you can add that under this item. And now we are ready to run the analysis. And if you click the run button, it will start running the analysis. And here I wanted to walk through all the inputs step by step, but another approach to get the exact same inputs filled in is to use our example tab. So here you can use example menu and click example 11 to populate all the examples. So if you just download EUQ and click this button and run example, it will still run and give you the same results. And then because it takes 1 hour, I ran analysis already last night. So once done, after like 1 hour, this is the user interface you will see in the results tab. So what it shows you is the name of engineering demand parameters, which was specified here. It's standard earthquake, meaning those are peak floor accelerations, peak floor drift, peak interstory drift. And 2 means it's the second story response. So because we have 9-story building, we have until PID 9. And this one in the end is indicating the direction, horizontal direction. But in this example, we have only one dimension excitation. So it's only 1 in this example. And then it additionally gives you the final estimated statistics from multi-fidelity Monte Carlo, including mean and standard deviation. And it again displays the speed of vector you gained. So some response quantity have higher correlation, so you have higher speed up, but some of them has lower correlation, so you get lower speed up value. But overall, you can see the speed up lies between maybe 5 and 15. And at the end, you can see that elapsed time is around 1 hour because we specified 1 hour in the beginning. And high fidelity model was evaluated only 35 times, and low fidelity model is evaluated like 1,200 times. And then if you go to data values, you can see all the samples created from low and high fidelity model. Here, it's kind of fun to play around with because if you want to compare the response from high and low fidelity model, you can directly draw scatter plot by clicking right button and then left button for another quantity. So it's comparing peak interstory drift of 9th floor from model 1, which is high fidelity model. And this is peak interstory drift 9th floor from model 2. So if your low fidelity model is very good, then the correlation coefficient will be very close to 1, as you see in this example. But if it's not, then you will see more of larger scatter. So by that, so this is just showing the exact same thing. And finally, I would want to discuss that this is post-processed plot that shows the error in the estimation. So blue one for each of the EDP quantities, and the blue one indicates its multi-fidelity estimator. Orange one is the estimation only using the high-fidelity simulation, and green one is the estimation using only the low-fidelity simulation. And as you can see, high and low-fidelity predictions have higher error, but for different reasons, if you remember correctly. The high error in high fidelity comes from small number of sample size because we can only run few number of simulations. That means if you can run 1,000 simulations using high fidelity model, the error will probably approach to 0. On the other hand, low fidelity model, we have enough number of simulation and we still have the error. And this is inherent bias that comes from the model, which is not as detailed as the high fidelity model in most of the cases. So this error will not decrease even if we include more number of samples. And to emphasize this fact, I ran another simulation, another one of this analysis with different random seed. And you see that the green bar, the low fidelity error is pretty similar because it ran enough number of simulations. The error does not change anymore very much, but the high fidelity error heavily depends on the random seed we specify. That's because we estimate this quantity using only few number of simulations. And the similar accuracy trend is observed for the second order moment. Second order moment is used to estimate the standard deviation of our response. So that was the part I prepared for slide. Remaining is the future plans for EUQ and COFEM in uncertainty quantification side. We are planning to have update our tools. Especially, we are trying to enhance our Bayesian updating capabilities by releasing hierarchical Bayesian updating method and surrogate-aided Bayesian updating method. The latter is to improve the computational efficiency. And also, we are planning to have reduced order model generator to help you develop reduced order model with less effort. So that later you can again import this model in either in EUQ or R2D and run your simulations more efficiently. And we have SimCenter forum. We would like to interact you with this forum whenever you have questions or bug reports. And this is our website. Each of our tools have a page, and this is the part where you can find all the links that's related to our tools. And also I want to emphasize that we have online UQ office hour every Friday noon. So if you like to talk with us, you're welcome to join. And then there are upcoming live expert tips on January, as well as in-person computational symposium that's organized. We are part of the organizer, so please feel free to register and join us. With that, I think I would like to conclude my presentation. Thank you so much for your attention.
Thank you, Songri. That was excellent. I think it was very informative. There are a couple of questions. Would you mind, I think we missed whether you ran the simulations locally or whether you ran them at Design Safe, at the high performance computing resources there.
Yes, this should, in my case, I ran it through our my local computer, but it should work on Design Safe as well.
Okay, so the hour runtime and the eight cores were just on your local laptop.
Yes, this example was on local laptop.
Okay. What are the different values of speed up mean for some of the different EDPs?
That's a very good question. So here you see different speed up for different EDPs. And if you see the speed up plot again, you can see that speed up depends on the computational cost ratio as well as the correlation coefficient. So different EDP will certainly have the same computational cost ratio, but their correlation coefficient can be different. For example, in our result, this was the correlation coefficient we get for, say, interstory drift of 9th floor. But say, let's see peak floor acceleration at 9th floor from model 1 and peak floor acceleration at 9th floor for model 2. You see that this one has weaker correlation coefficient. So here correlation coefficient is slightly lower and we see a bit of larger scatter. And that means PFA at 9th floor, we get lower speed up compared to PID at 9th floor, which had higher correlation coefficient.
Okay. Could you explain the speed up one more time? Is it a gain in the precision or of the estimates on the different engineering demand parameters?
Speed up is the gain in the computational time.
Okay.
So for a target accuracy, if you have a target precision, you can decide how many number of simulations you need to run using naive Monte Carlo simulations, as well as multi-fidelity Monte Carlo simulations. So this tells you if to match your target simulation, multi-fidelity simulation will require 1 hour of simulation, while Monte Carlo simulation using only high fidelity may require 10-hour simulation. So that's what speed up 10 means.
Okay. And then in the beginning of your input into the EEUQ tool, you put in a particular runtime. Can you
Yes.
go over how you came up with a 60-minute runtime to begin with?
That's partly because we knew about our model pretty well. So we knew that our high fidelity model simulation will require 1 minute, at least 1 minute per simulation. And we wanted to have at least 30 pilot samples. So that already arrives at like 30 minutes to run only the pilot simulations. And then at the same time, we knew that our correlation coefficient is quite high, so we will have higher reliance on the low fidelity model. So we expect we probably don't need to perform a lot more high fidelity simulation runs. So we were kind of approaching it as a trial and error, but it worked in this way. But we do plan to add one more display in the next release that shows expected number of simulations to achieve the target accuracy. So target accuracy is in terms of standard deviation or the normalized mean square error. Of course, those are expected error and error bounds. And based on that, we are planning to inform you how many number of simulations are, how much computation time is needed to make your prediction satisfy the target accuracy. So that is indeed in our next release.
Okay. Can the output of the low fidelity model be used as input to a FEMA P58 loss analysis? And I think then the question, the follow-up is, then can that be used as a sensitivity analysis within EEUQ to figure out which component of the structure, maybe the elevator or connections, are driving the losses. Is there an example of this using SimCenter Tools?
Yes, we do plan to link this, propagate this to PBE and other R2D SimCenter tools. But in that way, we are not gonna directly use the low fidelity simulation samples. But because this correction is done in the aggregated level, meaning mean is corrected instead of each individual samples are corrected. So because of that, we will probably need to assume that we are following log normal distribution. Our EDP distribution follows log normal distribution, and then we generate the samples of these EDP quantities, and then put those samples into the FEMA P58 analysis as input.
So let's take a step back. Maybe the question isn't related to the multi-fidelity Monte Carlo, but more generally about accomplishing performance-based engineering calculations with EEUQ and sensitivity. So I think the answer might lead more towards the PBE tool as a resource for running the FEMA P58 loss estimates, because yes, that is built into it already. And I guess maybe my question for you, Songri, is more about the sensitivity analysis on the losses, or on the component losses. Is that something that anyone's looked at within PBE?
Not really, but that's a very good point. That's probably the direction we need to push forward. But currently, our workflow for the sensitivity analysis or the advanced UQ algorithm arrives at EDP, and then it does not connect to the damage and loss assessment. So I guess answer is no sensitivity analysis. At current stage, sensitivity analysis can run through EUQ and for the EDP values and not for the damage and loss values. But if you are interested in doing that, you can, if you come to a UQ office hour, we can provide you some workaround, because we have another tool called CoFM, which is quite flexible. So there is a way to generate workflow using PBE and then import those workflow in CoFM, so that this then CoFM will treat this workflow as a black box model that gets some structural inputs, and outputs will be some damage and loss estimates. So that can be one possible workflow that we'll be happy to discuss.
Wonderful. Thank you for answering our questions, Songri. Thank you to the attendees for submitting your questions and for attending this live session. I want to remind viewers that you can register for our live expert tips and other events at our webpage, which is simcenter.designsafe-ci.org. This concludes today's live expert tips with the NHERI SimCenter. We hope you've been inspired to pick up this example that Songri presented and adapt the capabilities to your own research. Thank you, Songri.
Thank you, Matt. Thank you, everyone, for joining.